I want to remind you how one would do holographic computations of correlation functions, say at 0 temperature in Euclidean space. So this is a very standard thing. Now let's, so we are looking now in Euclidean signature, where a lot of the subtleties that we will be talking in details are not present, the subtleties of the Minkowski space. So, so here I'm going to write down the, say, what I need is to start from a background that describes the theory. So I'm going to use the z coordinate. So d mu dx mu. So I'm going to assume Euclidean signature, so that is plus. Actually, I'm going to write dt square plus dx square, d tau square, dx square here. If I want to have a black hole, I would insert some function f here. Let's stick with 0 temperature right now and remind ourselves how one can compute, say, correlation function of scalar operator. And for simplicity, I will be talking about a scalar operator that is dual to a massless scalar. That is, in this case of 4-dimensional theory, it will be a dimension 4 operator. So the action for the scalar field typically would have these forms. So I have d5x minus square root of g mu nu, d mu phi, d nu phi. And let me keep track of the coefficient in front of the kinetic term. So let's call that capital K over 2. And let's see how one can compute the correlation function of the operator O, where O is the operator that is that corresponds through the dictionary to this scalar field phi. So all that I'm going to do now is in the original paper by Gapser, Klebanov, and Polyakov. Following the ADS-CFT prescription, what we have to do is to solve the equation of motion. So the first step is to solve the equation of motion, which in this case has a rather simple form. Is equals 0, okay? With the boundary condition that when z goes to 0, the limit when z goes to 0 of this function, which is the function of z and x, where by x I mean these 4 coordinates along which the metric is translationally invariant. So this is equal to phi 0 at x. And then the ADS-CFT prescription tells us that in order to compute the 2-point functions of this operator, we need to insert the solution into the action, the classical action, and then differentiate with respect to the boundary condition. Okay, so in our case of a scalar field dual to a massless scalar, things are very simple. Okay, so what you can do with this equation is that you can make use of the fact that the problem is translationally invariant along this 4 direction x and solve the equation in momentum space. So you Fourier decompose the field in components phi of k z, and in terms of this the equation for each Fourier component are independent of each other. You have separate equation for separate case. In this particular case, I think the equation would look something like the z of 1 over z cubed phi dz phi minus k square phi over z cube is equal to 0. Okay, and this equation has exact solution. I'm not going to write the exact solution here for you.
This is a 4 plus 1 dimension.
It's just 3 plus 1 dimension in the boundary.
Changes in different dimensions.
Yes, so this one is in the, if the field theory is in 4 dimension, and this is ADS 5. Yeah. And in general, you have different power of z here. Okay, so and we have to solve that equation with the boundary conditions that phi kx kz goes to phi 0 of k when z goes to 0. So in general, we can think about this. Let's draw this function phi of z, z here. Okay, so this is a second-order differential equation which has 2 independent solutions. We have one boundary conditions at z equals 0. We need to impose another boundary condition, which in this case is rather obvious. The solution has to go to 0 as you coordinate z goes to infinity. You can think about, look at this equation. If you ignore this k square, it is just a wave equation with an imaginary frequency. So you have a solution that is damping with the behavior like phi equal e to minus k times z. In fact, the solution to this equation is just some modified Bessel function, and one of the modified Bessel function goes to 0. Okay. So and the dependence of the solution on the initial condition, on the boundary condition, is rather trivial because the equation is linear. So one can write phi of kx is equal to some function that I'm going to introduce here, f of k at z times f0 at function of k. Okay, where this f sub k function is is the solution to this equation, with the boundary condition that f of k at 0 is equal to 1. And this function can be obtained, and one gets if one expand that function in small z, it will have 1, but the next correction will be z to the 4 log z, I think k to the 4, and then plus etc., etc. But the exact form of this function is also known, so I'm just writing down the first coefficient in the expansion. So if I plot this as a function, if I draw the plot of f sub k as a function of z, it will start from 1 and then going down and then approach 0. Okay, and now we have to substitute that into the action. Substituting the equation, there's a solution to the equation of motion to the action. We find that we can do an integration by part and make use of the equation of motion and reduce the action into a boundary term. So basically, we pull one of the derivative to act on the other part and use the equation of motion, right? So S at the end will be equal to integral this k over 2, but the integral now is sit at the boundary of the space z equals 0 dx, and then we have r cube over z cube times phi and dz d phi over dz. Okay, is this step clear? When we go from this here to this one, you just do integration by part and then reduce the integral, reduce the bulk contribution vanishes due to the equation of motion. We are left with the boundary term after integration by parts. And the boundary of space is z equals 0. So here all the integrals sit at z equals 0, and you have this thing with a minus sign, which I don't know how to track. I could track it here, but I will lose it very soon. So all the equation here is up to sign. I will try to keep the factor of 2 correct, but the sign you have to forgive me with that. I think you are right. This is a minus sign in this case. And then we are doing the OO correlators by taking the derivative of the action with respect to phi. So instead of computing the correlator in coordinate space, I'm going to compute the correlator in momentum space. So I'm just okay. So here I have to differentiate with respect to the boundary condition. So I'm going to change that into momentum space instead of 2 pi to the 4, something like this. Time r over z. That actually has to be understood as a limit z goes to 0. You might be bothered by this 1 over z cubed. If you are bothered, then think about that as a limit z goes to 0. Z cubed. Now f of k star dz f of k. Let's see, f minus k dz f minus k phi 0 k phi 0 minus k. Okay, that I'm just inserting that solution into here and rewrite the integration over space as integration over momentum space. Okay, so after differentiation, one would find that the correlation function is something like k limit z goes to 0, z over cube of f minus k dz f of k. Okay, so and a momentum conserved delta function. Yeah. So I don't know whether it would be here. So k minus k. Yeah. So I'm here by this I mean the integral over dx e to I kx of x goes 0. Yeah. Okay, and let me remind you, if you do this calculation, you will find at the end that the correlation function is proportional to some number that depends on the normalization of the action. The momentum dependence is k to the 4th log k. Okay.
So if we consider, if you say the sk expression there,
Mm-hmm.
we take the derivative over z. We think of z cubed log later. Z cubed
Yeah, that
so how can I say?
that actually is log kz term. The singular behavior over k, the leading singular behavior over k is k to the 4th log k. The epsilon, yeah. So here I neglect the term that when you do naively the calculation like that, you might encounter terms that are divergent when you take z goes to 0. With these terms are all polynomial over k, and these are if you Fourier transform a polynomial of k into coordinate space, it's a delta function. So to compute to make this contact term precise, you have to do a more sophisticated computation. typically you would add the boundary term to the action.
So the contact term is precise, but it's not non-universal.
Well, it depends on how you define. If you, for given definition of the correlation function, there is a precise expression for it. For example, if I defined my stress tensor correlation function as the derivative of the partition function over the external metric, then this is a unique definition, and I should have a unique two-point function, and one can give the prescription, ADS-CFT prescription that would reproduce this unique this definition of the two-point function.
There's no cutoff dependence in that contact term.
For stress tensor, I'm not sure. Yeah, I have to think about it. Clearly, the imaginary part cannot it does not depend on the cutoff. So plus contact term. Which I will ignore. Okay, so it is just a review of what one does at zero temperature in Euclidean signature to compute correlation functions using the ADS-CFT prescription. Now, suppose I'm going to finite temperature and still ask questions about the Euclidean Matsubara correlation function. How one would do that? So the action remains the same. Now, what changes is the appearance of some factor multiplying the component of the metric here, where this function f of z is equal 1 minus z to the fourth over some z naught to the fourth. And that z naught is related to the temperature. Let me write down here how the temperature is related to z naught. Temperature, the Hawking temperature is equal to r squared divided by pi z naught. So when z naught goes to infinity, let's check, z naught goes to infinity, function f goes to 1, so that becomes the zero temperature metric. So let's look at this metric a little bit closer. So in Euclidean space, the coordinate z doesn't go all the way to infinity. When this function f becomes 0 at the horizon. So the horizon is z naught. So near z equals z naught, we are going to look at the metric near z equals z naught. So near z equals z naught, this function Did you have problem changing from R to Z when?
I use only Z and I didn't do finite temperature, so.
Okay, so my notes is mixed between R and Z, so I'm going to do it on the board here. So f of Z is equal 1 Z 4 Z minus Z naught over Z naught, right? Near Z equals Z naught, I have this Z. And then I'm going to call this Z naught minus Z. Let's call Z naught minus Z equal to some new coordinate. Let me call that the rho.
You want to switch to where you see the origin to smooth point?
I think I'm going to switch now to some coordinates that is in my note, so that I don't make any mistake. It's very easy to make a mistake here. So by a trivial change of the coordinate, you can rewrite the metric in also quite useful form, where R is now just a honest to God radial coordinate, okay, where R, f of R is equal to 1 minus R naught to the fourth over R to the fourth, and this relationship between R and Z is R equal R square over Z. Okay, so then let's do the computations right here. So let's say there is we are still in Euclidean space, so there is a plus sign here, and R runs from R naught to infinity. Let me look at the behavior of the metric near the horizon. The horizon is the place where this function goes to 0, and R equal R naught. So sorry for that. Okay, so let's say R equal R naught plus rho, and then you expand the functions. I think now I get it right. R naught plus R square, rho square, but I'm going to neglect the rho square. Okay, so let's look very closely to the part, the tau and the R part of the metric. When we approach the horizon, the component of the metric along this x direction, the spatial direction, are all finite. There is nothing interesting happening there. On the other hand, here we would have for R naught over R square, rho dt square, d tau square, plus R square d rho over 4 R naught rho. Okay. Okay, so the x dependence plus something that depends on x, but I'm going to ignore, not looking at it. I will not be looking at it because the metric components are finite, irregular at the horizon. This x component here is just R naught divided by R square, dx square. So this one is regular. What is more interesting are the part of the metric where the component goes either goes to 0 or to infinity. Yes?
So let me just make sure that I'm clear on this. This is not actually a black hole, this is a black brain.
This is a black brain. Yeah, it has translational invariant here, and there is, yeah. Mm-hmm. Yeah. Okay. Okay, so now, so let me erase this one. Okay, so by the way, if we now do another transformation, we can actually derive the Hawking temperature. If we say replace rho by new coordinates, let's call that rho tilde square, then you will see that the ds square will be equal to R square divided by R naught times d this rho tilde square plus you will have here 4 R naught divided by R square rho tilde square d tau square. Okay, if you look at this metric, you can recognize it using the method of staring at this metric. So it is just the flat space in polar coordinates. Rho tilde is the rho tilde goes this way, and the tau is the angular coordinates that go that way. Yeah.
Why is there 4 there?
It 4 comes from here. This 4 cancel out by the substitution. I think when you substitute that rho, you can d rho square here give.
Well, it's rho and not tau. We haven't fixed the periodicity.
Mm-hmm.
Oh, right.
So you fix the you now say in order for the horizon r rho tilde to be equal 0 to be free from conical singularity when the metric is smooth here, tau has to be a periodic variable that matches with the Matsubara formalism in field theory, where the Euclidean time has to be periodic, and using this method you can derive the expression for the Hawking temperature. Okay, so that's how it works. So in this case, what we have, we can visualize the metric in this way. We have space-time, where time is periodic, and then as we go along in the decreasing r, so this r equal infinity is here, r equal r naught. R equal r naught is a place where the metric terminates, but there is no singularity. Now, the calculations of the Green's functions can proceed.
The metric doesn't go inside the line, beyond the horizon. So
In Euclidean space, that's it. Yeah, that's a metric. It's the part, the metric here, would looks like what I'm drawing on this figure. Yeah, and then the time coordinate is periodic. The metric doesn't have horizon per se in Euclidean space. It's just the horizon is just the place, the maximal radial coordinates that the metric would have. So in this case, when you solve the equation would change the form. The form of the equation would change a little bit. Here, instead of k squared, you would have, I think, you had something like omega over f plus q squared. Phi is equal 0. And then here you would have another f. That would be the modification that you need to put into the equation of motion of a scalar field. And you know what kind of boundary condition you have to put here. Since the metric is capped off like this, it's smooth here, you have to impose the boundary condition that the scalar field is regular at the this mode function has to be regular here. Here. Okay, and that's what fixed the.
So
Yes.
is there also an expression for the entropy in this Euclidean formalism?
I think you can compute the action and then identify the action with the partition function.
The Einstein action of the
Yeah, yeah. And then you will find you have to differentiate the action with respect to time in order to find the entropy. It's like doing quantum field theory in Matsubara formalism. The partition function is the exponent of the free energy. Right? So the classical action here would map into the free energy.
So what is Zm that replaces your Z equals 0?
Right, so it's equals 0, so it equals Zm. So, yeah, this maximum value of Z.
What is Q?
Okay, so here the K has decomposed into omega and Q. Yeah, so it's the Euclidean momentum decomposes into that. So here the prescription is rather straightforward and can be implemented for the calculation of 2-point functions in Euclidean space at finite temperature. Okay, so now let's go to the main part of my lecture. It will be about computing real-time correlation functions from ADS-CFT correspondence. And before doing the calculation, I want to give some motivations and some outline of what we are going to see when we do this calculation. So we know that there is the gauge gravity duality establish the equivalence between two objects. If we the quantum field theory in one side and some gravitational solution on the other side, if we put the correspondent at non-zero temperature, we would have a non-zero plasma, some QFT plasma is put into a correspondent with the black hole or a black brane solution. So for the case of n equal 4 super Yang-Mills theory, we believe this correspondence is exact and is becomes simple in the strong top coupling limit. Now, as I mentioned, as I told you in the previous lecture, a finite temperature plasma in the low frequency limit, omega and k, q goes to 0, reduces to hydrodynamics. And hydrodynamics, we can see hydrodynamics behavior only in real time. This is intrinsically a real-time phenomenon, the existence of the low energy hydrodynamic theory. So that means that the dynamics of this black brane, this hydrodynamics, should be encoded in the dynamics of the black brane. So if we do the calculations of, say, correlation function in the black brane horizon, and then we take the low frequency, low momentum limit, we should reproduce hydrodynamics. So there must be some non-trivial connection between general relativity on the background of solution with the translationally flat horizons, the black branes, and the hydrodynamic theory, and that is what we are going to try to see. Okay. I think Shiraz Minwala will be also talking about the connection between hydrodynamics in gravity in his lecture. Okay, so now I'm going to switch the signature of the metric to minus, plus, 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 and then try to describe how everything would work there. So now time is not periodic, and we can think about the analogy with the real-time quantum field theory. The time in the closed time path formulation of field theory goes from minus infinity to plus infinity. We don't have periodic time here. T is not periodic. Okay, so let me concentrate now on these equations. Suppose we are proceeding in a way that is the exact copy of what we do in Euclidean time, and write down the equation of motion for the scalar field. We will get an equation that looks like something like this. I believe there is a minus sign here, plus sign, minus q square. F. Okay. And there is a subtlety of this equation, of the solution to this equation, that would we can see that subtlety if we look at the behavior near the horizon. Let's take near horizon limit. Where f goes to 0. Okay. Z goes to Z naught. F goes to 0 linearly, but I will keep just f in the equations. So when f goes to 0, we can see this term is not very important. If the frequency is non-zero, this one will always dominate the q squared if we go close enough to the horizon, so I will ignore that. So roughly speaking, the equation will become something like this, dz of phi. Let me naively put z equals z naught here, and then neglect the z. It's correct when we analyze the behavior of the solution near the horizon. So the equation looks something like this. Okay. Now let me introduce useful coordinates that would be an alternative radial coordinate that will be useful in the future. It's called the tortoise coordinate. I don't understand why it's called tortoise. But not turtle coordinate. R star is defined so that f of z d over dz is equal d over dr star. And let me check the sign. I want when z goes to the horizon, I want r to go back, so minus sign. Okay. So from that you can easily find out what is r star. Since this one goes to 0, the function f goes to 0 as z naught over z up to some constant, so you can find out that near the horizon r star is simply 1 over alpha logarithm of z naught minus z with a minus sign, I think. Okay. So, and then the equation of motion now becomes a simple wave equations. Rather simple wave equation, right? So this coordinate r star is introduced so that at the horizon it goes to minus infinity. So at the horizon it goes to minus infinity at horizon. So basically we stretch out the coordinate so that instead of the radial coordinates going to a constant at the horizon, it actually goes to minus infinity. Okay? And decreasing the rate, this r star decreases as we go to the horizon. Okay. Let's see. Here I'm. You can see here I solved the equation in the coordinate, not in momentum space, in coordinate space. So omega square is replaced by dt square.
The fact that this is dependent on Q, is that a very general feature?
It's a rather general feature of the horizon. At the horizon, nothing depends on Q. You actually seem that the black hole horizon is fragmented into points. It's the quantum field theory at different points are independent of each other. There is time living on the horizon, but not the different points in space are not communicating.
From the perspective of
It's a good thing, yeah.
Not a good thing.
It's a good thing for something.
Okay.
Yeah. But for hydrodynamics, it is actually. I think it's a good thing that the hydrodynamic behavior is coupled to that particular horizon. Okay, so now if these equations can be solved very easily. The solution to the equation of motions are just plane wave solution. Phi equal e to minus I omega t minus t star plus r star, and phi equal e to minus I omega t minus t r star. There are two solutions, plane wave going in this direction and plane wave going to the other direction. So let's see how they would look like. So here I'm drawing the picture of, so here's the boundary, here's my horizon. And if I've solved the equation, so the ADS-CFT prescription tells us that we have to solve the equation of motion with some fixed boundary conditions. So here is phi of r. What I see is that the solution becomes an oscillating function because r star goes to infinity, goes to minus infinity at this point. The solution oscillates like with more and more oscillation as you approach the singularity. Okay, so when you solve this equation, you have two solutions, and none of them, neither of them are more regular at the horizon than the other. So, so at this point, it's clear that we have to do something more sophisticated in order to understand, to resolve this apparent ambiguity with the ADS-CFT calculation. Right. So the problem here is that we have two solutions, and they both oscillate. They are complex conjugate of each other. If we delete this frequency part, they are just complex conjugate of each other. But they both goes to they both behave the same way. Okay. So the way we the correct way to do an ADS-CFT calculation in real time was suggested by Maldacena. And it's a very interesting. We see here a very interesting connection between thermal field theory and the closed time path formulation of quantum field theory. That was also been suggested previously outside the framework of ADS-CFT by Bekenstein. By Israel. I'm sorry. By Israel. By Israel. Okay, so the thing here, the important thing here is that the horizon is a place where the coordinate, some coordinates become singular, but it is not a singularity of space-time. We can continue the space-time past the horizon, and let us do that and see what we recover when we try to go through the horizon. Okay, so unfortunately I have erased my one of my previous equation, but it looks, I will reproduce it here. Remember that we have written down, when we said R equal R naught plus rho, we found that the R naught rho over R square minus dt square. I'm in the rho dt square R square over 4 R naught rho. Okay. rho is r minus r naught. I'm going to write the metric not in terms of this rho, but I'm going to write it in terms of this tortoise coordinates r star. Okay, and using just doing elementary change of variables, you will find that this is 4 pi r star times minus dt square plus d r star square. Okay. So it's rho basically is this difference between the coordinate and the position at horizon of the horizon. So it stays in this rho becomes an exponent, and the rest is just looks like the up to this constant factor. It's just a flat metric. And now I'm going to introduce so-called Kruskal coordinate.
That metric to the r star, it's obviously not an expansion in small r star, but or is it?
Yeah, it is an expansion of a small r star. I'm just looking.
Near the horizon.
Sorry?
But how can it go near the horizon? And then this could be expansion what? Small.
R star goes to infinity. Near the horizon, R star goes to minus infinity. Right, so
And
that.
so that metric is valid for what values of r star?
For all for R star where the R star larger negative. So let's think. Yeah, let's think about that this way.
Everywhere it's valid, you're near the horizon. In some
Yeah.
of the original coordinates.
The original coordinates written here. Actually, you can do a more sophisticated change of variables. Near the horizon, it will reproduce. It will reduce to that form. Yeah. The Kruskal coordinate is defined this way. So I will be using this formula later. So I will write it in a protected box. U equal minus e to 2 pi t, t minus r star, and v equal e to the power 2 pi t, t plus r star. And again, by the method of staring, you see the metric near the horizon is written in terms of u and v is just du dv, right? It is basically, one can rewrite this as minus dt's Kruskal square plus dx Kruskal square to bring it in a more familiar form. If we think about this u and v as the light cone coordinates, so then u would be t Kruskal plus x Kruskal, and v would be t Kruskal minus x Kruskal. The metric, going through this change of variables to Kruskal coordinate, yes?
Isn't there a sign mistake in your formula for u and v? Like, shouldn't it be r star minus t and r star plus t?
Minus t. You're right. Yes, minus here. Yeah. Thank you.
This is all outside the horizon. The original coordinates.
So the
Are all the coordinates
as we define it right now, the original system of coordinates has real t and real r star. So u is negative and v is positive. Okay. So, but this change of coordinate tell us that the point where u or v or u and v are equal 0 is nothing special from the point of view of the metric. We can actually near this horizon is basically where the metric is flat. There is everything is smooth. Okay, so using the Kruskal coordinate, we can continue the space-time past the horizon. So I'm going to draw this diagram where the Kruskal time defined this way goes upward. U going this direction and V going in this direction. Okay, so time, basically the Kruskal time is this direction, and is this coordinate is Kruskal coordinate x is pointing this direction. The system of coordinates that we use previous to introduction of Kruskal coordinates, the coordinate t and r, or t and z, or t and r, r star cover this part of the metric. U, if t and r are if t and r are real, u has to be negative. That's correct, and v is positive. That's also correct. So previously we are living here, and there is an event horizon that we did not step through. The event horizon is the border of this space. There is some boundary here. Let me draw it this way. So let me draw it like this. This boundary correspond to z equals 0. It was outside the range of validity of this formula, because here the formula is valid at only at r naught, that is largely negative. But topologically there must be a boundary. Our previous boundary is some line here in this Penrose diagram, and then using u and v coordinates, we discover that the space-time has this Penrose has the structure of the space-time is more complicated than we thought. In particular, there is another part. There is another word where the Kruskal coordinate changes sign. This is the metric here is an exact copy of this one, but here u would be equal to plus e to minus 2 pi t minus r star, and v would be minus e 2 pi t plus r star. But time and space here now is the time and space in another word here. And this part of the Penrose diagram would also have, we can also draw a boundary here, another boundary. The suggestion of Juan Malacina is that these two boundaries are where the sources, where the quantum, these two boundaries correspond to the two part of the closed time path contour. So recall that in quantum field theory, thermal quantum field theory, one formulation of field theory that we went through previously is the formulation through a path integral when the action is taken over a contour in time, and the contour make this detour into the Minkowski time. So this part of the contour would correspond to the upper part of the contour, for example, would correspond to this to the boundary of the right quadrant of the Penrose diagram, and the left-handed contour would correspond to this lower part of the closed time path. The left boundary correspond to the contour, the lower contour. You can see that this time t goes upward in the right quadrants, but the time we define here would go downward, like this, corresponding to the two part of the contour having time going opposite way. Yes?
This choice requires sigma, the separation and imaginary time of those two contours to be made over 2.
Yes. We will see that the way that I'm going to do it, we would reproduce the the thermal correlator defined with sigma equal beta over 2.
So inserting sources is like a first control, and the other source is a lower control.
Yeah, would be corresponding to imposing boundary condition for our field on this part of the contour and this. The sources are not, but as we will see, if we have a source J1 here and a source J2 here, then the value of the field in the right quadrant, for example, would depend not only on the source on the right part of the contour, but it also depends on the source that we put on the left part of the Penrose diagram. So the field, the solution to the field equation will depend on the source on both sides. Well, we are solving the equation of motion with a boundary condition.
What if we insert the sources to one sources to one boundary? Like if we want to calculate G11.
We will calculate G11. We would insert a source here, and then take the source here to be 0, right? Yeah, but
so right now the solution of phi should take over.
Yeah, we have to solve the equation in the whole space. You see, if you look at this way, we fix the boundary condition here, and we fix the boundary condition here. Okay, so on the two boundary, the field is fixed. We solved some kind of wave equation between these two boundaries. What we're still missing actually now is that we still have to impose the initial condition. And what happened when the time in this Penrose diagram goes to minus infinity and plus infinity?
Why that equals to sigma equal to beta over 2?
We will see that it's so here you can already see that these two part looks similar. So there is a certain symmetry between these two part of the Penrose diagram. If we compute the 2-point functions, where one source is here, the other source is here, it will be a symmetric 2-point. The Green's function will be a 2x2 matrix, but it will be a symmetric 2x2 matrix. And in thermal field theory, we get a symmetric propagator only when sigma is equal beta over 2. Only there we have G12 equal G21. Okay.
What is the justification for this proposal in the end?
The justification at the end is that it works. It satisfies the correlation function that you compute will satisfy fluctuation dissipation theorem.
So, in other words, if I analytically continue the Matsuhara answer, it's guaranteed to equal
to be the retarded Green function that you get from this prescription. Yeah.
So another way to think about it, just for the plateau, you can see the fully contractified plateau as well. You can actually include all the slices, and then just like you fully contractify your space-time, the boundary space-time, then just exactly the same thing.
Then you can smoothly connect it to the original thing with the closed-off space-time.
Yeah, exactly. Yeah, just the contractified plateau space-time naturally fill in the fully contractified the boundary space-time.
Let me solve the equation of motion, and then describe the what I alluded to as the initial.
Historical remark of that is Werner Israel first realized this. There was a boundary condition that Hartleb-Hawking prescribed for black holes in order to get thermal Green's function that satisfied the KMS boundary conditions. And Israel realized that was a vacuum state, a boundary condition, defines a vacuum state in quantum field theory, and that vacuum state was defined on the whole Kruskal manifold on both sides. And then Israel pointed out that this looked exactly like what you do in thermal field theory with the closed path, where you make the thermal density matrix by correlating the system with a copy of itself that's going backward in time. So he said that must be what
That must be what happened.
wave function is.
I see. So it's also related to Holography.
Yeah.
Yeah.
This is the Holography matrix.
This is the Holography matrix.
Yeah. Okay, so now we are going to solve the equation of, since the metric is so simple, the equations for scalar field will be du dv equals 0, or phi. There are, again, in the Kruskal coordinates, there are two types of solution. There is wave, there is plane wave that goes to the left or to the right in this picture. So let us see this plane wave. So let me fix in this Kruskal coordinates. Let me look at all possible plane waves. So suppose I have a frequency that is bigger than 0. Then I can write down 4 possible solutions. E2 minus omega u, okay, E2 minus I omega v, E2 plus I omega u, E2 minus I plus I omega v. Okay, so I look at these 4 particular solutions to the plane wave solution. Let's recall that u and v's are just t Kruskal plus x Kruskal, and you see the usual plane wave right away, minus I omega t Kruskal minus x Kruskal. And I'm going to classify this solution in using 2 criterion. One is whether the frequency is positive or negative. Positive or negative. And another criterion whether it's an incoming wave or outgoing wave. Okay, I might okay, so look at this first equation. So first plane wave would have minus I omega t. So in my convention, E2 minus I omega t with positive omega is positive frequency, and the wave's going like this. So it's going out from the horizon, so it's outgoing. U is t plus, let me see. U is t, so if x is here, let me draw x here. U equals 0 correspond to x minus. This is actually plus. Yeah, it's actually plus. For some reason. Okay. U equals 0. No. U equals 0 is x t. So I made a mistake here actually. Yeah, minus. U equals 0 correspond to line here. Yeah. So yeah, minus. Yeah. Thank you. So it's outgoing, and you look at other waves. You see clearly this one is frequency is will be positive frequency, and it's incoming to the horizon. This one is negative frequency, and it's outgoing. and this one is negative frequency, and it's incoming waves. Okay, so what we allowed? I'm going to declare the following, and that amounts to the choice of the vacuum state in the quantum field theory in Kruskal coordinate. That this and this modes are okay, but not this one and this one. The positive frequency modes have to be incoming, and the negative frequency modes are outgoing. So to be very sketchy, if you recall one of the equations that you see in quantum field theory, it's the mode expansion of a scalar field, e to minus ikx, ak e plus e to ikx, ak dagger, C plus, yeah, this is like this. And then the positive frequency mode coupled to the annihilation operator, and the negative frequency comes in the creation operator. If you translate that into what you need to impose for the classical solution to the wave equation, that corresponds to allowing only incoming positive frequency and outgoing negative frequency mode. So we are going to find solutions that are linear combinations of these two particular type of plane wave.
So in and out refer to or from the horizon?
To and from the horizon. Into the horizon.
It's into and out from.
Yeah, and out from the horizon. So I'm going to classify the mode using this Kruskal time and this Kruskal space. And one can think about what does it correspond to in the two sides, and I will have to.
In the middle of the space, not kind of in the past and the future, or is that not true? Are these way in the past?
Okay, in this thing, I think I'm actually putting the boundary condition at t and x in the middle. That's you're right.
Middle of the space. Is that right? Is that the condition?
No, you just require the wave function is fractalized horizon, so that's your fractal function.
Right. The equation, but there's something that I myself is I don't know the answer to. Maybe when I go to this place, you can explain to me why that choice is has to be done. If I solve the equation in the original coordinate, I will find the solution. So in the t and r star coordinate, I find solutions that are, for example, I will find a solution. There are two solutions as we talk about. Let me call that f of k. So there are two solutions, e to minus omega t, f of k of r, and e to minus I omega t, f of k star of r. We talked about them before. This one is e minus I omega t minus star t star, like this. And it is minus u to the power of I omega divided by 2 pi t. Okay? And this one, using the same thing, is v to the power of minus I omega over 2 pi t. This is e to plus I omega t plus r star. T plus r star. Where is that? This you just look at the Kruskal coordinate and then translate this plane wave. The solution in the previous coordinate in the right quadrant, they lead to this solution. Now, what does it mean? Is that this at u equals 0, this solution actually there is a branch cut in this function, and to say that the solution is regular near the horizon, we have to know which way we put in which half plane we put the branch cut. In which half plane we make the solution to be analytic. So I think this condition single out uniquely how to analytically continue this solution from the right into the left. Right. So yeah. So that's correct.
Yeah. So you want the positive frequency modes on the left, on the right quadrant to analytically continue to the positive frequency modes on the left quadrant. And the definition of the positive frequency modes is that the modes should be analytic in the lower half plane, and so let's determine that choice.
Right. Okay. So.
Why do I have to do the upper half plane? The upper half plane will be the negative frequency mode. So you want the mode to be yes. So the definition of the positive frequency mode is that it's analytic.
Okay. So let's talk about that here. So we have single out. Let's say we single out these two modes, right? But the general solution is a linear combination of these modes. It's some with different omega. We assume here omega is positive, so it's a general solution is a sum over this exponent with different positive omega. And if we look at this as the as function of complex omega, it is analytic in upper half plane as a function of u, and this is analytic in lower half plane. In V. So taking any wave, any exponent, and make the imaginary part of omega positive, this one goes to 0. So clearly, a linear combination of these should be analytic. Okay. The two solutions here, yes, near horizon. So actually, I am here. I'm trying to put the condition on how do I analytically continue a solution that exists only on the right horizon that are written here. I want to analytically continue them to the left or to the left. So it is on the right quadrant. And this function, I have to, so it's minus u to this power, and I have to analytically continue, keeping u all the way in the upper half plane. Then in the right, what one would find is u to the power of I omega 2 pi t times e to the power of omega divided by 2 pi t. And with this one, translate into minus v to the power of I omega minus pi t into minus omega 2 pi t. It's the right left, yeah, on the left. Yeah. And so this is the condition of analytic of continuity. On the right hand side, if we solve the equation, say we solve the equation for phi, we know that the solution of the wave equation is a linear combination of two solutions. They can be incoming or outgoing wave. They can be this one or this one. with different coefficients. K plus beta k times f k k r times the boundary conditions. And right now we don't know how to fix these alpha and beta. The only boundary condition we have now is that at the horizon, at the right boundary, phi has to go to phi naught. So, which means that alpha k plus beta k would be equal to 1. Yeah. If we normalize this function so that they are equal to 1 at the boundary, right? Now, this should be phi 1. Now, what we say here is that in order to formulate this procedure, the source here, the boundary condition we put here is that phi is equal to the source on the right-handed, on the upper part of the string, of the closed time path contour. Translated into this language, that becomes, if we analytically continue to the left-hand side, we would have phi of k equal alpha k e to omega divided by 2t f k star of r plus beta k e minus omega over 2 pi t f k r. Okay, and so, and that should be, let's see, I might be making, so let me erase this thing here. Put that to be equal to phi 1, okay? So I take away this. So in order for this to go to phi of 1 of k when r goes to infinity, or equivalently z goes to 0, I need alpha plus beta to be equal to phi 1. Here I would have to impose the condition alpha of k e to omega over 2 pi t plus beta k. Actually, there is no t. I make some mistake in here. Yeah, by pi. Yeah, by pi. Yeah. 2t. Yeah, t e minus omega over 2t is equal phi 2. So from this, we will, the complete solution to the equations is possible. We have alpha k and beta k, which you can solve as expressed in terms of phi 1 and phi 2. We will solve that next time, substitute that into the action, and find down the real-time correlation function. One thing you can already see here is the appearance of the thermal factor omega over t everywhere. Actually here omega over 2t, indicating that the contour that we have has this sigma equal beta over 2. And we will check that the correlation functions obtained in this way are reasonable, thermal correlation function, and then compute the retarded Green function for the stress energy correlation function.
So phi 1 and phi 2 are the two boundaries, is that what?
Yes, so phi 1 and phi 2 will, in field theory, are the source. Phi 1 is equal to the source that coupled to the operator on the two contour, and alpha and beta now solved as a function of as in terms of phi 1 and phi 2.
So there are the two solutions that are differential equation fk and sk star, and you take some linear combination.
You have to take some linear combination, yeah, and the linear combination, which one is picked, depends on the condition you put at the horizon. Okay. Thanks. No more questions?